Hello everyone, once again I welcome you in my fourth lecture of three-phase inverter. I am Dr. Arunima Verma from Institute of Engineering and Technology. Today I am going to deliver a lecture on three-phase inverter, which I already am continuing since three lectures I have already described about what are the different modes of inverters in which three-phase bridge inverters in which they work, how the Fourier analysis is done, and how the comparison is being drawn for 120-degree mode and 180-degree mode. And the drawback of these, though these modes are very simple, they are very easy to implement, but then the major drawback of these two modes of operation, that is 120 and 180, are is basically the output voltage which is available is absolutely fixed in and constant in value. You cannot change the output voltage, and in certain industrial applications, as I had already told you in lecture 3, that we require control of output voltage in our hands. Like say we have certain industrial applications where we require three-phase speed control of three-phase induction motor. Now, to have certain kind of such speed control of induction motor, so obviously in that situation we require an input voltage to have an equivalent amount of speed which is to be obtained from that induction motor to meet out the load demand. Now, so basically what happens is, to this induction motor is fed from three-phase inverter. Now, this three-phase inverter provides AC supply to the induction motor. Now, in this case what we do is, whatever input voltage is required, say if we have 1400 rpm, we require 1400 rpm in induction motor. So, equivalent amount of voltage should be available at the input of the motor, so that 1400 rpm is obtained at the output of the motor. Now, to have that much amount of voltage, the inverter output will be again the same, because the same three-phase inverter is feeding the induction motor. So, again we require, after some time we require 1500 rpm, or we require 1495 rpm. Then in that situation we require increased value of voltage, so which generates 1495 rpm. So, you see that in such applications, like we have say printing press, we have rolling mills, and we have so many we have hospitals. In hospitals, lot many variations in output voltage is desirable. Now, if we have control on the output side, definitely we are going to achieve that one, and to achieve that one, that means to achieve the output voltage controllability, we use certain kind of techniques which I already told you and elaborated in lecture 3, that is PWM, pulse width modulation technique, and I already explained one of the types, that is single PWM. In this lecture, we will go further and describe certain types, second type, that is multiple pulse width modulation. Now, in multiple pulse width modulation, as you can see the waveform, we have carrier signal as the triangular signal, which has got now one component, amplitude 1 was already present in single PWM, which the component which is added in multiple PWM is the frequency of carrier signal. Now, in this case we have two components which are present, that is, one is the amplitude and second one is the frequency. Now, the orange part, that is orange waveform, is the reference signal which has got again an amplitude AR and frequency FR. Now, this reference signal will be compared with the carrier signal, which is triangular in nature, as you can see. Now, earlier in single PWM, what had we had carrier signal in such a way, or rather you can say it had a fixed frequency. So, in such a way that we obtained only single output or single pulse in each of the half cycle. Whereas, in this case you can see in multiple PWM we have an advantage that we get number of pulses in each half cycle. More the frequency of the carrier signal, that means if you are increasing the value of Fc, that means more number of pulses will be available at the output of the inverter. I have shown you here directly the output of the inverter V0, which is available alternate in nature and with number of pulses available. Now, one special feature again in multiple PWM you can see is these pulses, although this is not very evident from the waveform which I have drawn, because it is a you can say it is a handmade waveform, not very precise, but this is very particular, because you have to keep in mind that the pulses which are available are of the same width. That is very important. These pulses, be it this one or this one or this one, they are of the same width. That is very important. Although number of pulses are available, but each of the pulse that is available in each of the cycle, they will be equal in width. Okay. Now, again, by varying the value of AR, by changing the value of AR from 0 to AC, there are two ways. There are two ways of comparing. Either you change the amplitude of reference signal from 0 to AC, and the second method is you can change the amplitude of carrier signal also from or bring it down to the value of AR, and wherever it cuts AR, you get a pulse available over here. Now, we are taking this one, we are changing the value of AR from 0 to AC, and accordingly the width of the pulses will vary. Is it clear? So, again you have to keep certain things in mind. Every time I say this word, because these are very important points from the point of view of examination, from the point of view of objective questions as well. In case of multiple PWM, since we have a frequency factor, as you can see FC and FR, which are present both in carrier signal as well as in reference signal. So, during this period we have one more modulation index which is defined over here, which is frequency modulation. We have FC upon FR. FC again is, I already told you, FC is the carrier frequency signal, and FR is the frequency of the reference signal. Now, in this case, one parameter I have shown here is this F0. Now, this F0 is basically equal to FR. Now, you will say, what is F0? Now, F0 is very simple. F0 is the frequency of the output voltage which is available at the inverter side. So, obviously, now here you can see what I want to derive or what I want to conclude from this, that if you change the value of reference signal, you will definitely have a varied value of the frequency of output voltage inverter. So, basically FR determines F0, that is important. Now, to the frequency of reference signal, as I already told you, the reference signal frequency determines the inverter output frequency. Say, for example, in India we are having 50 hertz, we all work on 50 hertz, and if we want to have a supply, AC supply at the inverter side of 50 hertz, so definitely we have to, in PWM technique of this multiple type, we have to keep the frequency of reference signal as 50 hertz, very simple. Now, in this case, now you will say, what is the significance of then carrier frequency signal? Now, in case of carrier signal frequency, basically it determines the number of pulses which are available in each half cycle. Now, you will say that what does the number of pulses have to do basically in each half cycle? If we are having, say, 5 pulses in each half cycle, or we have 10 pulses in each half cycle, how does it matter? But basically what you will see, that by increasing the number of pulses, basically if you increase the number of pulses, you can see over here, the fundamental that you will obtain will be more precise, or you can say more equal to sinusoidal, near to sinusoidal. So, by increasing the value of the by increasing the value of number of pulses, that means if you increase the frequency of carrier signal, you are going to increase or generate more pulses in each half cycle, and that will help in reduction of harmonics, number one. Secondly, it will not, it will reduce the distortion as well. So, in this way, if you see, in multiple PWM, this has got an added advantage of multiple PWM over single PWM, that with the help of number of pulses available in each cycle, we can have the reduced harmonic content automatically without going through further analysis. Now, how do you determine the number of pulses? That is very simple. You have frequency modulation index, which is divided by 2. So, you get this as the number of pulses which will be available in each half cycle. So, in this case, you have these many parameters which you have to keep in mind. This is very important, this is important, and this is also important. Basically, these two things you have to keep in mind, and these are the formulae. And the modulation, amplitude modulation index, as it was applicable in case of single PWM, it will be applicable in case of multiple PWM as well. That is, the modulation index will remain the same for say M, which is defined as a ratio of AR by AC. AR is the amplitude of reference signal, AC is the amplitude of carrier signal, that is AR by AC. This is amplitude modulation index, or you call it depth, you can call it whichever fact. This is there. So, in multiple PWM we have an advantage, we have two advantages. Number one is we have two types of modulation available, that is, we can vary the value of amplitude, or we can vary the value of frequency as well, and we can have different types of facility available. Now, in case of sine PWM, this is the third type which we are going to discuss. This is one of the most eminent, or you can say the most widely used PWM technique in industries. Why? Because the name suggests it is a very common thing which you can guess that sine PWM, why is it so widely used? Because in this case the reference signal is basically sinusoidal in nature. So, obviously, we do not have to give it from anywhere else, we do not have to put a function generator to generate a step output or a rectangular signal. We just have a sine AC supply available, or we just have AC available any side. So, we can generate sinusoidal, and we will compare this reference signal, which is sinusoidal in nature, with the carrier signal. Now, in this case, everything will remain the same as it was there in multiple PWM. We will get the number of pulses in each half cycle, because the carrier signal frequency is available, and this carrier frequency signal will determine again the number of pulses in each half cycle. Now, what you have to keep this in mind is in case of sine PWM, this is very important, that whatever pulses are available, they are not in they are not at all having equal width. They are unequal, they are having unequal widths, and you have to keep this in mind, right. In sine PWM, because this sine wave has instantaneous value, and the value or the amplitude varies at each point of time. So, whenever it cuts the reference signal, the pulses which will be available will have different width, as you can see. Now, in this case my diagram goes very good, because handmade diagram, you can easily recognize that the width of the pulses are different. Now, to come up or sum up with the various PWM techniques which I defined or elaborated in my lecture 3 and current lecture, we have this basically single PWM, multiple, and sine PWM. These are the reference signal which you have to remember, that in case of single PWM we have rectangular reference signal carrier. Now, this is common this is common basically. Rectangular and triangular reference carrier signal are common in single and multiple PWM, whereas in case of sine PWM, basically the reference signal will change, which is sinusoidal in nature, and this is easily available. So, sine PWM is one of the most widely and most commonly used PWM technique. Second point which you have to keep in mind is pulse of equal widths are available in each half cycle. Now, in this case single PWM, so obviously you will have only one pulse available in each half cycle, whereas in case of equal widths, again in case of multiple PWM, although we are achieving number of pulses, but pulse of equal widths are available. In case of sine PWM, we have number of pulses available, but we have unequal widths available of each pulse. See? Next is single pulse in each half cycle, as I already told you, name also suggests the same. So, name goes by the number of pulses which are generated in each half cycle. Simple, if you have one pulse, it is a single PWM. If you have multiple pulses, you have multiple PWM, and if it is a sine one, then you have sine PWM. Now, in this case, since single PWM, we have only one pulse available, so there is no question of frequency. So, we have only one modulation index defined, that is amplitude modulation. So, we will use only this part, that is amplitude modulation will be used. In case of multiple and sine PWM, we have both the parameters involved, that is you can say amplitude and frequency. So, obviously, we have both AM and FM techniques which are used, that is amplitude modulation index will be used as well as frequency modulation index will be used. Now, width of the pulse determines the output voltage magnitude. This is very important. This is unanimous in all three cases. That means it is common in all three cases. That is, width of the pulse is determined by or determines the output voltage magnitude. Basically, if you change the value of the width of the pulse from 0 to pi, you will have output voltage magnitude varying from 0 to E. This is in all three cases. Next, we have this one, that is single PWM. In single PWM, we have reference signal frequency determines inverter output frequency, which is common in all three techniques. That is multiple also you will get the same one, and sine PWM also you will have the same one. That means the frequency of the reference signal will decide what will be the frequency of the inverter output voltage. And in case of multiple and sine PWM, we have carrier frequency. The role of carrier frequency is also there because it determines the number of pulses which are required in each half cycle. Say we want more number of pulses, we want n number of pulses. So, we will have frequency equal to n in each half cycle. So, accordingly, we will see that how the carrier frequency plays an important role in generating the pulses in case of multiple and sine PWM. Now, the last point which I have already told you is single PWM, the number of pulses are fixed. Number of pulses are fixed, that means you have only single pulse which is available in each half cycle, whereas in case of multiple and sine PWM, you have to see that by increasing the number of pulses in each half cycle, you tend to decrease the harmonic content. That is very important because harmonic is one of the you can say most important parameter or one of the most important factor which are involved in power electronics devices. Whenever I already told you in my first lecture itself that whenever we go for power electronics devices induction in any system, it has got an inherent tendency to generate harmonics which is harmful. Basically, it distorts the fundamental component, that means the sinusoidal waveform which is ought to be available is not properly available because it involves harmonic content as well. So, the mitigation of harmonics, the elimination, the reduction, everything, the research is going on to in this direction to how to minimize or how to reduce the, how to eliminate the harmonic content from each of the waveforms, so that we are more near to basically sine wave. So, in case of sine PWM, we have very important factor which is known as distortion factor. In case of sine PWM, if we are using sine PWM, we will get this distortion factor automatically and significantly reduced, as it eliminates all harmonics less than 2p minus 1, where what is p? You will definitely ask what is p. So, I will say p is basically the number of pulses which are available, that is number of pulses which are available in each half cycle. So, if we have say 5 pulses or say we have 5 pulses available in each half cycle, 5 pulses available, then how much harmonic will be reduced? 2 into 5, that is 10 minus 1 up till 9th, up to 9th harmonics, all the harmonics will be reduced in case of sine PWM, that is the biggest advantage. So, as now you can see, if you increase the number of pulses, more number of harmonics you are going to reduce. Say for p is equal to 11, if you have 10 number of pulses. So, 20 minus 1, that is up to 19th harmonic content you can easily remove in case of sine PWM. Now come to the, we are talking about so much about PWM techniques. We say that it is this, it is that, it is this and that. So obviously we should go through the advantages of PWM technique, and the first major advantage for which we employ PWM technique is basically this one, that we are able to control the output voltage of the inverter. That is very important, well, from the point of view of various industrial applications. And secondly, we can all automatically have output frequency control as well in case of inverter, and these both two parameters, that is voltage and frequency, can be controlled within the same power block. That means you won't have to use one power block for output voltage, or you won't have to use one power block for frequency. Second advantage, which is an added advantage of PWM technique, is it reduces harmonic content and even eliminates lower order harmonics, as we have already seen. This is important, how we eliminate the harmonic content, that is by analyzing the Fourier analysis. We extract the harmonic part, and whichever harmonics we want to reduce, we simply equate it to 0, and we get that particular harmonic as the width of the pulse will give you, if you adjust the value of the width of the pulse, that is delta, to that particular angle which we have obtained from the Fourier analysis, we will definitely eliminate that particular harmonics. For example, if we want to eliminate third harmonics, we have to put delta is equal to 120 degree, or if we want to eliminate fifth harmonic, we have to put delta is equal to either 72 degree or 144 degree, and so on. So this eliminates, and it eliminates lower order harmonics. Why I say like this? Because this sine PWM, as I already told you, it has a capacity to eliminate all harmonics below 2p minus 1, where p is basically number of pulses available in each half cycle, not full cycle, it is half cycle. You have to keep this in mind. Then next advantage is, since it is reducing the harmonic component or harmonic content, so obviously the size of the output filter to which will be required in the system will be less. Obviously size will be reduced, so you will have a reduction in system cost as well. This output filter is basically filter that we use that utilizes inductor and capacitor as the components, LNC, which are expensive in nature. So, if you reduce the size or rating of the output filter, you will automatically reduce the system cost. The fourth is, after achieving all this, this is but obvious that you are going to achieve this, because this improves the reliability and efficiency of the system. Obviously, when you have voltage control in your hand, when you can reduce the harmonic content and you can get more of sinusoidal waveform, you can have more fundamental sinusoidal waveform, you can reduce the size of the output filter. So, obviously, these two parameters automatically are linked to the above part, and reliability and efficiency of the system automatically gets improved. PWM logic. Now, this is basically the most fundamental part, because we are using computers like anything. We have so much of so many microprocessors being used, and advanced versions of nowadays microprocessors are available. So, PWM logic, since it can be generated using microprocessor, number of components get reduced. Obviously, when you are having MUPI, so you just design it and program it, and you will have PWM technique available, rather using different types of components, going for number of components. So, this as number of components get reduced, so the complexity of the power circuit block or the control circuit block also reduces. Finally, the limitation of PWM, after talking about everything, that we have so many advantages of PWM, we have so many advantages of PWM and so on and so forth. The limitation every thing which is generated in this world, any technique, any method, any everything has got advantage and disadvantage, and the major disadvantage of PWM technique is that maximum frequency of operation is limited due to higher switching losses. That means, as you increase the value of frequency, definitely you will get better output, but at the cost of what? Having high switching losses. So, with this we come to an end to one particular and one important technique, which is known as PWM, which reduces the output voltage and reduces the harmonics in this inverter side. Now, we come to another important part of three-phase inverter, which is also known as a rather inverter, we can say, because this kind of inverter are both available in is available in you can say single phase as well as three phase. We talk about till now we were discussing everything about voltage source inverter, where we used to give a DC voltage source. Now, this DC voltage source had certain disadvantages. So, obviously, we went for current source inverter. Now, in current source inverter, what we do is we generate a DC current. How we will generate a DC current? Because DC is not available in any nook and corner. So, we have to generate DC by a three-phase converter, and we will whatever three-phase converter is generating, that will be feeding an inductor, high value of inductor, and this high value of inductor combined, basically this part combined, gives you the definition of current source, this one. That is a three-phase converter which you are using. Basically, it is a voltage source, and it is converted to current source by connecting it in series with a high value of inductor. So, this forms a current source, and these are the SCRs which are connected in the fashion shown. You get the SCRs 1 and 2. Say for example, at instant A, you are going to basically fire SCRs 1 and 2. Instant O, you will fire SCRs 1, 2 are fired. ठीक? Now, SCRs 1 and 2 are fired, so you get the output like this in first cycle. Now, SCR 1, when 1 is conducting, it will charge C1 and C2 with these polarities as shown. See, capacitor C1 will be charged with left plate polarity, whereas C2 will be charged with right plate polarity. Now, now in this case, this is done in a fashion, this is basically a commutation circuit is also involved. Whenever you will fire SCR 3 and 4 at instant B, when you will fire SCR 3, 4, as you can see from here, you will see that this SCR 3 instant B, SCRs 3 and 4 are fired. Now, these SCRs 3 and 4 will turn off SCRs 1 and 2, as you can see over here. Before that, the capacitor is fully charged with left plate positive, and the capacitor basically this does not allow these diodes do not allow the capacitor to discharge themselves, and in this case you have C1 and C2 which will be helpful in basically turning off or acting as a commutating component for SCRs 1 and 2. In the same fashion, if you want to turn off SCR 3 and 4, again you are going to fire SCR 1 and 2 at instant E, and alternately you get the output voltage. Now, the direction of the load current basically determines the direction of the output voltage which is available during period OC. You get the direction of current in this fashion, and whereas in case of during period C E, you get the direction reversed from this side. Okay? So, you get the direction of the sun. With this, I just gave you an introduction of current source inverter. This is how we obtain the current source inverter. These are the advantages, as you can see over VSI. Instant inherent techniques are already there. So, no overload protection is there, commutating inductor is not there, it is not required, small size filter required and all that. So, this basically efficiency is improved. With this, I hope that this lecture has given you a feedback of CSI and VSI in an elaborated manner. Thank you very much for listening once again to my lecture. Thank you.